happy to introduce Ilyas, who will tell us about hardness of the cosine neuron by cryptographic tools.
Yeah, thank you very much, Alex. Okay, so, well, thanks a lot for the invitation. It's great to be talking about this recent work we had. So it's kind of, I think, morally really lies, in between kind of hardness of inference and cryptography. And yeah, I think it's a good match with the workshop. So this is a joint work before I start with Joan Bruno from NYU and Mijay Song from NYU. Mijay is also around. And it's going to be discussing the hardness of the cosine neuron. So this is a problem that, we kind of coin it like this, but has been studied actually already in the inference and machine learning literature. But like we get a new insight on how hard it is actually via cryptography. Okay, cool. So let me start. So, okay, so what's the cosine neuron? Well, morally in the statistics language, it's a generalized linear model. It has some small caveats in it. So let's start by properly defining it. So it requires, first of all, two parameters. So it requires a beta, which is the noise level if you want, the noise parameter. And it requires also a gamma. So a gamma is what we call the frequency parameter. And what happens is, if you really want to think of these parameters, if you don't want to think of them as just free parameters, you should think of them, they could be dimension dependent. And you can think of it as gamma being, for example, like d squared or d third, like some polynomial function in d, which is at least square root d. And beta is just a shrinking noise level parameter. And then what happens is we also have a certain signal, W, which is just uniform on the sphere. Okay. None of these three parameters we know, okay, when we are making the observations. So we know beta and gamma, and there is this hidden W as well. And what happens is, we try to learn, if you want W, or to make some learning of a certain function in the following fashion. We receive n samples, and the samples are received in the following form. So each sample is received in the following form. We sample, first of all, an isotropic Gaussian in 2 dimensions. And then what happens is there is a certain noise, xi, that xi is just a small number, arbitrary number, but it's at most beta, and that's the importance of the noise level beta. And then what we do is we observe y sub I, which is the cosine of 2 pi gamma times the dot product xi dot w plus this noise. Okay, so let's try to understand what this says. So it says yi, you're observing this number, which is just the projection of w across xi. So it's the inner product between w and the xi, which is a tropic Gaussian. And then, okay, it's just you apply a certain activation function to it. And the activation function to it is just the cosine activation, but it has a small catch. It also multiplies it with this frequency parameter. Okay, and what is released, right? So what is the cosine, right? So the cosine, looks like this, if you want. Like with this is like, pi over 2, and it has period 2 pi. So what happens with, this is the cosine of t. The cosine of gamma of t is essentially the same thing, but like it really like makes it much more oscillatory, and the period becomes 1 over gamma. So you can think of it like this. So it's like an activation where it's much more oscillatory than before, especially if gamma is like dimension dependent. Like here I try to, as I said, to imagine at least square root d. It's like it's like a very small 1 over root d, let's say, period. Okay. Cool. So this is the setting, and we receive n samples of this. And the question is, whether you can use these samples to make some inference of W, or you will see also like certain learning setting of this function class. So just a comment. Look, this model has appeared before, and it has appeared also in a slightly different variant sometimes, where you just make the same observation, but you put gamma inside W. Okay, so for V equal gamma times W, you're observing yi, which is the cosine now activation, times the xi dot v plus xi. It's really the same model. It says now v is not in the unit sphere. It could be of norm gamma, where gamma could be polynomial large. So it's like, it's kind of the same model. It seems, okay, it seems like that the activation is just cosine, but you hide it in the norm of v. So it's like just the same model. Okay, so what do you want to do with this inference model? You want to use the sample to do 2 tasks. So the first task is to recover W. Okay, so like to recover W is the parameter recovery. So like, you want to use the data to recover W, from, and because there is certain ambiguity of the cosine is an even function. you cannot actually distinguish between W and minus W. Cosine of t is equal to cosine minus t. So like you want to just have little vanishing distance from W or minus W. And also a second task is a weaker task, so strictly weaker task. So if you have this, you immediately have this, is to weakly learn the function you're getting adversarial samples around. So like to produce a certain G hat that on Gaussian input, X, isotropic Gaussian input, it produces something which is close to the original cosine you're trying to learn for these parameters gamma and W. And how close? Well, you want to beat kind of the trivial estimator, which outputs the mean of this, if you have no information, by some constant advantage. So by some constant level. Okay, so these are the two tasks of the cosine neuron. Like you're receiving samples, n samples of them, and you want to see, can you use these n samples to parameter recovery, or even weaklier to sort of do weakly agnostic learning of this cosine function. Okay, and you know, of course, like this is the statistical question, but what is the computational question is whether you can do this in polynomial time. That is whether you can choose n to be polynomial in D, and also you have a polynomial time estimator W hat or G hat that achieves these goals. Okay, and again, now notice that like the important parameters here is beta and gamma, because everything, the prior is uniform on the sphere. So essentially everything is defined by these two parameters, beta and gamma. Okay, so that's the cosine neuron. Okay, so why do people care about this model? Like, why is this model interesting in the first place? Before we start discussing about why, whether it's hard or not. So, this is just the model again. Y is the cosine plus a little bit of noise, but the noise could be adversarially small, but like of cardinality at most beta. Well, the thing is that cosine neuron is kind of relevant to the question of learning one hidden layer neural networks. Okay, first of all, you can think of it as a trivial neuron itself. That's why we call it a cosine neuron, where like, you are having a neuron just with a different activation than usual. But then, okay, you can say, okay, this is not really the right thing to do. We want ReLU activations. And, there is approximation results. So like, because exactly cosine is a Lipschitz function, and it's a Lipschitz function, you can prove and bound the Lipschitz function. You can really prove that like there exist certain scalars, so that for any polynomially many number of the samples, really what the cosine produces is really close to the performance of a certain one hidden layer neural network with width, which is polynomial in the dimension and the ratio of the frequency and the noise. Okay, and error at most beta. So let me say this again. You can just use standard approximation results to say that like for any polynomial many samples, even exponential samples, you will get from the isotropic Gaussian Xi. What will happen is that this value is very close to the value of one hidden layer neural network, and very close meaning at most beta. Beta is the same beta on purpose. Like the error is at most beta from a hidden layer neural network that where you pay everything in the width, and you do not pay really too much. You pay polynomial in gamma over beta. And okay, so if this is clear, gamma is, as I said, polynomial. Think of it as polynomial in the dimension. And then it all depends if you choose beta inverse polynomial, let's say, or like exponential, but like everything, if beta is inverse polynomial in the dimension, as we will see, it's really like a polynomial weight that simulates the performance of the cosine. In other words, what I want to say is that learning this cosine neuron with adversarial noise, actually it's equivalent with learning this specific neural network with adversarial noise as well. And why is that? Any sample from this with adversarial noise beta of level at most beta is really a sample from this with adversarial noise 2 beta. Right? I mean, because of this inequality, and vice versa. Any sample from this neural network with adversarial noise of value at most beta is really a sample from this with adversarial noise at most 2 beta. So in particular, anything you want to do with these samples are exchangeable, and of course also the final testing of the weak learnability is also exchangeable. So that's why the adversarial noise here becomes handy, because it allows you to go from one model to that. Okay, so people have noticed this. And of course, like there are two implications here. One implication is if I have an algorithm that learns the cosine neuron with adversarial noise, I can immediately say I have an algorithm that learns the neural network with adversarial noise. But that's actually not super interesting, because it kind of tells you that this specific neural network can learn in polynomial time. Okay, I mean, it is interesting, but maybe it's not like super interesting because it's very specific. What people really care about is the negative implication. Okay, the negative implication is if I have some reason to believe that this cosine neuron with adversarial noise cannot be learned by some class of algorithms, then I have an instance of a one-hidden layer neural network with Gaussian input that cannot be learned with adversarial noise, right? And therefore, the whole class of one-hidden layer neural networks with corresponding polynomial width in gamma over beta and D just has one example that is hard to learn. So that's kind of the motivation for why to study it. Okay, so hopefully this is clear. Then the next question is like, okay, is this hard? Is this actually a hard problem, or like, you know, this negative implication just is meaningless? And it turns out that you know, it actually seems hard from prior work. So it seems to be a hard problem to indeed learn with no, and surprisingly, even with you have no noise in the system. So even if you didn't have this adversarial noise in the first place, we have reasons to believe this is actually a hard problem, at least for natural algorithms. And there is this paper by Ohad Samira 2017 that proves that actually gradient descent on actually not just the population landscape of this cosine neuron, but actually even in a big family of landscapes, which is quite expressive, but still, you know, certain family of frisks, of loss functions, will actually require, even with no noise, exponentially the gamma square iterations to essentially move in the direction of W. And okay, that's kind of an interesting result because gamma, again, think of it as a least square D, you need exponentially in the dimension iterations to even start moving, essentially in a direction that, you know, involves non-trivial W. Okay, so that was the first result Ohad Samir had in 2017. That kind of, you know, it's in the same spirit, that somehow it essentially says, aha, so this seems indeed hard to learn from gradient descent. And this is no noise. Then there has been some other result that studied this model again and said to prove that for certain Lipschitz SQ queries, and for a certain weak, admittedly, class of them, subclass of them, yet they were able to prove that there is a lower bound. So somehow, like, they were able to refute a subclass of SQ algorithms, even again with no noise if gamma is at least root D for this model. So yeah, long story short, it kind of seems hard. So like this is this was the status. It kind of seems hard. We have some reason to believe it is hard. And you know, the natural question is like, you know, can we actually understand this gap better? So can we make sense of it better? Like it seems a relevant model that like it has implication on neural networks. Can we actually say something more about its hardness than these results? And you know, more specifically, you can ask for which noise levels is cosine neurons actually hard for gamma at least square root D? It seems that beta equals 0 could be a choice, right? So like kind of the status seems to be that based on these results, like if somebody comes to you know, makes this axis, which is the 1 over beta, so somehow this is the signal to noise ratio, right, of the model. So somehow the larger the SNR, the easier the problem it is. You know, we kind of see that like it seems that it is gradient descent hard, and for some subclass, it is also SQ hard, all the way to here, all the way to the 0 noise. And okay, so the question is like, is this actually accurate or not? So now is where cryptography comes to the game. So cryptography allowed us to actually see that there is actually much more here to say. So it's a much richer landscape of hardness than what this picture is suggesting. Okay, so this work, actually, we have like a bunch of results in this landscape. Okay, so let's see. So, okay, this is the same axis as I have it here. So let's see. So like first we have like, okay, this is kind of joining for me like this, the one part of the semester here, which we try to quantify kind of what is in inference is hard or not. And the thing here is we're doing this through cryptographic tools. So this is the connection. Okay, so let's see what we're able to say using these cryptographic tools. So first of all, okay, there's a result, which is cryptography independent, of course, which is where can you hope to be able to recover, okay? So like when can you hope to be able to learn? Like for which noise levels? Like, okay, obviously if the noise is super large, if you're like very far there, it shouldn't be the case. And, you know, just maybe it will be good to keep somewhere the model to refer to it here. Right, so what is the cosine neuron again? right? And xi's are normal, ci's are arbitrary and at most beta. So like, for which beta do you have some hope to recover? I claim if beta is at least 1, you have no hope to recover, right? Cosine is in -1, 1. So like, if I can move them arbitrarily, I can really move every observation to 0. So like, of course, if beta is 1, you cannot recover. So somehow we have this result that somehow if beta is very small, but smaller than a constant, but small constant, then actually it is possible to be an exponential time algorithm and polynomial samples. So this kind of makes this zone clear that this is the regime we should be looking at. Okay. The second result is about the hardness of this model. So like our second result says that actually what's going on here is actually for all the regimes now where beta is inverse polynomial in the dimension. So like if this beta here now is allowed to be 1/d to the 10, let's say, or like, or of course constant, but like 1/d to the 100, there is actually some very potentially strong form of hardness related with cryptography and the known problem as shortest vector problem. Specifically, we can prove that if you are able to solve this inference problem for any noise level which is inverse polynomial in the dimension, we can actually prove that there is a reduction from worst case gap SVP with polynomial dimension factor, if that means anything to you, to this problem. So essentially, if you are able to solve this problem, you will solve the worst case gap SVP problem, which is a lattice problem. It's a lattice problem in algorithmic theory of lattice problem, in a regime where cryptographers don't believe that there exists a solution. There exists a polynomial time solution to it. So essentially, this suggests that this problem is actually enjoys some kind of strong form of worst case hardness in it, which to my experience, we haven't seen in such inference models like generalized linear models, which have this smooth activation function before. That like it's and Gaussian input, of course, and et cetera, like I think it's kind of interesting that somehow it's in this regime. It's not the case that like some subclass fails, but somehow if you find an algorithm, you will solve the problem in cryptography that like somehow it's believed to be hard. And how do we do this? We do this via essentially using and exploiting this new result on continuous learning with errors. Okay, we'll get more in details with this. Point is, we corroborate the existing lower bounds, right? We make a case that this is not coincidental. If the gradient descent was failing or SQ hard for some SQ classes, indeed there's a reduction to a worst case problem. We believe it's hard. The second thing, though, is kind of surpasses the existing lower bounds and actually says that, like, actually, if beta now becomes inverse exponential in D for an appropriate here notion of exponential, okay, like actually there is a way to solve this problem in polynomial time. So there is a way to solve this problem in polynomial time via the Lenstra-Lovász algorithm, which is a famous algorithm in the theory of lattices. And we actually understand exactly the complexity. I will come back to it later when we enter the stage with T+1 samples. And how do we do this? Maybe it's interesting also. We do this by essentially reducing this problem to a random subset sum problem. Okay, so subset sum is an NP-hard problem, but somehow by some breakthrough work by Lakarios, Zotlisko, and Friis in the 80s, which again known in the cryptography, so it belongs in this community again, like we know how LLL can send a random input distribution to polynomial time of subset sum. So how we make a connection between this consigned neuron and random subset sum, which maybe at high side is not obvious, and somehow we algorithmically leverage it to solve this problem to this regime. And this kind of surpasses the existing lower bounds in gradient descent and SQ. Okay, and that's kind of the main message of this talk. So what I'm going to do now is I'm going to explain for you, first of all, some lattice theory. So like, because it's not in the cryptography community, people are very familiar with it, but like less in inference of like, what is some lattice background and, what is this LLL algorithm and what is this gap SVP problem? And finally, what is this continuous LWE? And then I will come back to it with this background a little bit, with of course a very short background, and tell you about this result and then the reduction and then about the LLL result, and then conclude. Time permit. Okay. Cool. Let's see some lattices. So a lattice is defined as following. So lattice means a lot of things in mathematics, but for us, like it means the following things. So if you have m vectors in d dimensions, which are integer valued, that are linearly dependent, the lattice spanned by B1 and Bm is really the set of all integer combination of these m vectors. Okay, that's what a lattice is for us. So pictorially, if you have B1 and B2 to be two vectors, a lattice spanned by B1 and B2 is really like these blue dots here, right? So like this is the two-dimensional lattice generated by B1 and B2. Okay. What is the shortest vector problem? The shortest vector problem really asks you to solve this following optimization problem. It tells you, give me a base of the lattice, and I want you to output the vector with the minimum L2 norm possible that is in the lattice and it's not zero. So you can easily prove that any lattice contains a zero vector in it by just taking all zeros in the linear combination. So this is always in. The question is, what is the shortest vector besides this? And this picture here is here to convince you that like it could be hard, right? So even in 2 dimensions, if they're very aligned, of course not aligned, but like very close, V1 and V2, then somehow finding 3V2 minus 4V1 is not like a trivial task. Okay, so like even in 2 dimensions, you can get a feeling that like this is not an easy problem, and it turns out it's not. So it's NP-hard at the mild assumption. NP-hardness is actually NP-hard to approximate in almost polynomial factors. And to approximate, I mean solve the gap SVP, which is to find the value of the shortest vector. It is believed, and that's the assumption we will rely on. It is believed to be hard, though, to approximate even for any polynomial factor. Okay, and that's a worst case problem. And I'm telling you that like this is an assumption that like a lot of lattice-based cryptography is based on, which is that like it's actually cryptographically hard. As we say, it's hard to approximate up to any polynomial dimension factor. Okay. Yet there is this fantastic algorithm, this LLL algorithm, the Lenstra-Lovász algorithm, that can solve it in polynomial time up to an exponential dimension factor. So like LLL algorithm is doing the following thing, is giving the base of the lattice and outputs some x hat, which is also the original SVP, finds x hat, which is in the lattice, but it's not zero, and outputs something which in L2 norm, it has 2 to the d over 2 factor from this minimum shortest vector. And it runs a polynomial and d and the number of bits to describe the basis. Okay, so we believe it's hard in polynomial dimension. That's the worst gap SVP problem. We don't believe it can be solved in polynomial dimension approximation factor. And LLL can do this, can find a short vector, but in a seemingly huge approximation factor. But nevertheless, you can do wonders with it. Okay, cool. What's the continuous layer with errors? So the final thing for the background. So let me define it for you. So it's a recent CLW, I was going to say, it's a recent work of Minjae and co-authors, which is essentially defines the following thing, which is the following. So there exists, the resemblance with cosine neuron is not coincidental. I mean, I present in a way so that like looks similar for some reasons. So there exists again beta and gamma. So beta is again the noise level. Gamma is again the frequency parameter. And think of gamma as at least polynomial, at least root d, and beta is shrinking. And then you have again a W, which is a uniform signal on the sphere in d dimensions. And then you receive n samples. Now the samples look a little bit different, okay? So compared to the cosine neuron. So you sample an isotropic Gaussian again. And now you sample a small Gaussian with variance beta square, xi prime I. And then what happens is you receive labels Zi, which takes the following form. You take the projection of W on Xi, or on Xi, you multiply by the frequency gamma, you add the small noise Xi prime, which is distributed as this normal with variance beta square, and you take the fractional part of it. Okay. Cool. So why would you do this? I mean, if you come from a cryptography like this, it's going to make sense from the learning with error perspective, where you take mod Q here, and there's some discrete aspects. But nevertheless, this is what you do. Of course, it's a less nice activation function than the cosine, but it is what it is. That somehow like you receive labels of this form. That like it's a projection plus a little bit of noise, and you lose the integer part. Okay, so the goal in CLW is a detection goal, a decision goal, as people say in cryptography, about detection and inference, which is detect better than random with polynomial advantage, let's say, between receiving polynomially many samples of this form, where Xi is, so it's a generalized linear model again in some way. So you have the Xi, which is isotropic Gaussian, and you receive labels of this form. So detect between the CLW samples and the null samples. So the null samples are samples where you receive xi, and for the label, you do not take this. You take just an independent uniform fractional part. Okay, so like the goal is receive, in other words, the goal is the polynomial time goal is the following: receive polynomial many samples from this distribution that, like, you may be motivated or not to see what's going on here, and find some polynomial time statistic that separates it from samples which have xi, but then this thing is just arbitrary, just a coin flip, if you want, like a random distribution in minus half. Not a coin flip, like a uniform distribution in the fractional part. Okay, why would you care about this CLWE? This work of Brunner, Regev, Sok, and Tang. Well, it provides a very, very nice framework to do like this reduction, for example. But there are, of course, other. Hopefully, you will care by the end of the talk in other ways as well. But like like just as this, it provides a toolkit to do a reduction from the worst case gap SVP with polynomial dimension factor. So like there is a reduction that says if gamma is at least root D, and now parameters start being mattering, gamma is now at least root D, not think of it, it is at least root D. Beta is inverse polynomial dimension, 1 over D to the 10. Then if you could solve this decision problem, this detection problem, better than random for this beta and gamma, then this result is telling you that immediately there is a quantum polynomial time algorithm that solves this worst case problem, this worst case gap SVP problem with polynomial dimension factor that people do not believe it can be solved in even quantum polynomial time. Yeah.
There's a classical polynomial algorithm, there's a quantum polynomial algorithm.
Yeah, so this reduction is actually using quantum steps. So like even if it starts with a classical algorithm, it will turn it into a quantum algorithm.
Okay.
Yeah. But it believes to be quantum resistant, this assumption. Yeah. Okay, and that's kind of the background. Okay, so now let's start getting into the cosine neuron. So like getting into the cosine neuron, let's start with the reduction. Let's see like what what exactly can we say here. Cool. So this is, remind you again, the cosine neuron. I have it all also here for the people here. So like in the live audience, so like we're seeing yi, which is the cosine plus xi, and xi now arbitrary. So that's the thing. Okay, so there's this following theorem we have that for this cosine neuron now, we should have this smooth activation of the cosine now, not the mod 1. If gamma is at least root D and beta is inverse polynomial in the dimension, then if you could solve this thing with beta and gamma, for specific beta and gamma, which is inverse polynomial in D and gamma at least root D, then we can build a classical, again, polynomial time algorithm for CLWE with almost the same beta and gamma, up to a factor of logarithmic factor. Okay. And then you can use the result, and therefore there exists a quantum polynomial algorithm for worst case gap SVP, which we don't believe it exists. Okay, and that's kind of it's actually a simple statement, actually simple reduction also. But let me make some comments. Implication using this analogy with one hidden layer neural networks is the following. There is cryptographic evidence based on the worst case gap SVP problem that actually learning one hidden layer neural networks of polynomial, if you just plug in this estimate and the approximation I told you in the second slide, where the width is given by polynomial D and gamma over beta, you just take gamma over beta, where gamma is polynomial and beta is inverse polynomial. There exists one hidden layer neural network of polynomial width with isotropic Gaussian input and a load adversarial noise per sample 1 over polynomial. That like if you are able to learn the parameters of it, let's say, or if you are able to weakly learn it in the sense I said in the first slide, then you will solve the worst case gap SVP up to polynomial dimension factor. And that gives a strong statement that at least this class of any class of neural networks that contains this is probably not amenable to the polynomial time method. Okay, and just as a comment, cosine is not really needed here. So any periodic and or constant Lipschitz function, activation function, instead of the cosine here is working. It's enough for the reduction to go through. Okay, cool. So maybe I want to give you a small idea of the reduction. The reduction is simple and it kind of follows, I think, the intuition of how you should do this reduction, and the problems look similar. Again, the cosine neuron is this: you receive these samples, and and you want to, let's say, to weakly learn this function cosine 2 pi gamma x dot w, where x is Gaussian. And CLW is about detecting between receiving these now samples, like gamma times the Snare product plus Gaussian small noise mod 1, and detect from labels which are just noise in polynomial time. So like, how do we show that if you have an algorithm for the top, you have an algorithm for the bottom? The key steps is as follows. So first of all, there's actually an easy transformation I'm going to show in the next slide that transform any CLW samples with parameters beta and gamma. So any sample, let's say we live in the CLW is the top row. So like any sample where xi is standard Gaussian and zi is just this mod 1 operation of this inner product. If you give me any label zi, I can deterministically create a label for the cosine neuron. Okay, with parameters almost the same, and this is where you use the logarithm. So like, if you give me a bunch of samples from CLWE, I can create a bunch of samples with for the cosine neuron with almost the same parameters, keeping the same W. So the W of this and W of this is actually exactly identical. So like, just take a deterministic mapping of this label I'm going to describe. I can go from CLW samples of the top row to cosine neuron samples. Then I can use this successful algorithm that I assume its existence of for the cosine neuron to actually weakly learn this function. Okay, so this allows you to claim if I have samples from the top row. So this is a detection problem, it's a decision problem. So we're not done. But I'm just telling you that if you give me samples of CLWE of the top row, I can do something and transform them to cosine neuron samples, and then leverage the successful algorithm I assume its existence of to do something which is weakly learning this function, which involves essentially W. I forgot the gamma here, gamma and W. The second part of the proof is showing that if you were receiving here noise for ZIs that does not include anything about W, this whole channel breaks. That somehow, if you give me ZIs that do not contain information about W, it's kind of obvious from information theory point of view, like you transform into noise again, this F doesn't have anything to do with W. And this successful algorithm just cannot beat it doesn't have any information about W. Okay, so it all boils down then, how do you transform the samples of CLW to cosine neuron samples? And this is where the fact that it's periodic and ellipses comes into the game. How you transform a CLW sample beta comma gamma to a beta square log d comma gamma sample. Okay, so how do you transform this label to a cosine label? Well, it's quite simple. You apply the cosine. Okay, so like you apply the cosine and you hope for the best. The reason you apply the cosine is because cosine, it's periodic. Okay, so cosine is a periodic function. So like, even if your label is only keeping the fractional part, cosine only again sees the fractional part. So this is really the cosine of the original thing. Even if it doesn't have the integer part, just doesn't matter for it. So like, the moment you notice this, you're like, okay, cool. So this is the cosine of this plus this. And now how do you get out of this cosine from inside to outside? You use the Lipschitzness. So like, this cosine is essentially the cosine of 2 pi gamma xi dot w plus something order, and order is 2 pi essentially, but with some constant here, right? So what is the Lipschitzness here? It's just, the Lipschitzness is constant here for the cosine, it's just 1, basically. The ellipse is constant. And, some number here, which is at most the absolute value of the xi prime. And, because xi prime is at most to be at most beta, and you have a bunch of samples i's which are Gaussian. So xi prime I are standard Gaussians with mean 0 and variance beta square. Like the maximum of them is beta square root log d. So you have polynomially many IID rows of the Gaussian. In short, yi, it is a cosine neuron sample, but here you don't have, you have some understanding of what this is. We treat it as adversarial noise of value at most this. It's not really adversarial noise though, right? It's really coming from a normal with a different variance, if you want. Like if you just do the math, but we'll not quickly do it, but somehow we just say this is a number at most beta square root log d. So it's a cosine neuron sample with some xi. Okay, and then you do the trick I told you. From this label, you apply the cosine neuron algorithm and learn something about W or about this function class that you could not do if you were starting from from the null. And that's the kind of the reduction. Okay, that hopefully gives you some idea of like, and you can see here, we just use periodicity, ellipsisness. So nothing is hidden. So everything, let's go through. But that's morally what's going on. Okay, details matter, of course, and blah blah blah. But the morally, that's the whole idea. Okay, and that's again the theory. The like, yeah.
So are you saying that morally, learning a cosine neuron should be hard even with like Gaussian noise then? Because
Should be
like,
what?
like learning a cosine neuron where this psi is Gaussian should also be crypto hard by this sort of reduction, like morally.
I think Gaussian, yes, but with a different variance. So like if you just see what's happening here, this is a Gaussian, but like it's multiplied by something. And this something depends on the position of where you are, right? It's the sine of this, the derivative of the cosine at here. So like, yeah, but you say whether we could hope that we get rid of this annoying thing. That's what you're saying?
Sort of, maybe, but okay.
Yeah,
but I see.
I don't know. I think it's an open problem. I would think, I don't know. Actually, yeah, I don't know. If it's like, if you just follow this simple thing, this simple recipe, you get some annoying W-dependent term. It's not that somebody is trying to trick you though. So not really adversarial on the other hand, right? I mean, it's really like some position-dependent random noise. But
yeah, makes sense. Okay.
Yeah. Okay, so this was the second part. So just to convince you that like here we have actually a strong evidence leveraging essentially the conditional WE. Here is where the work was done. This is a connection with like a kind of, you can say technically easy connection you can make between the two models. Okay, so what's going on here? Like what is this? Why LLL is successful in this regime? Like while gradient descent and these algorithms were failing. Okay, so let's give you a theorem for the success. The success says essentially what this thing, it formalizes it. For any gamma, actually, we do not need magnitude D, any gamma you want, and any noise level which at most exponentially small, and D+1 samples, okay, so like one more sample than trivial, I would say. Then an LLS-based algorithm, it's in, of course, terminates polynomial time, recovers W or minus W, of course, up to error in L2 order beta. Okay, so that's the statement. You can recover using D+1 cosine neuron samples with small noise. You can actually recover in polynomial time the hidden W. And this in contrast with the gradient descent failure and SQ weak. It's for a subclass of Lipschitz SQ queries, like this is not possible. And this kind of puts something new into the game. And in particular, because beta is exponentially small, it implies directly the weakness. So we do even parameter recovery if you want. We can learn this W or minus W in this regime. And okay, so let's just reflect a little bit on the theorem. So if beta was 0, right? So this is the noiseless case where still the lower bounds apply. Then we say we can do exact recovery in polynomial time with D+1 samples. Okay, why do I keep on saying one more than trivial? If you didn't have the cosine here, which blurs the image, you will have linear equations. So you need D linear equations to learn W. So what this is saying is with one more than trivial, and of course you enter the cosine, you lose the sine, okay? But what it's saying is with one more samples than this, you can really invert the whole thing. Okay, in polynomial time, which I think is interesting, like in its own right. And some implications this theorem had. This PR, okay? So for noiseless phase retrieval with D+1 samples, like a noiseless phase retrieval is a famous inference, I think, where like, what happens is like you receive W along the projection with Xi and you lose the sign. And you ask if I get IID samples of this form, where Xi are sample of the time IID isotropic Gaussian, how many do I need to recover this W or minus W again? Well, from this theorem, you can just apply the cosine on both sides and get a sample of the cosine neuron, right? Again, because cosine is even, it doesn't care if you lose a sign. So you apply cosine 2 pi gamma y, you get a sample of 2 pi gamma xi dot w, like it's the same thing for cosine. And by applying this theorem with D+1 samples, you can recover W or minus W. So this gives an answer to the noiseless phase retrieval problem that D+1 samples are enough. Again, obviously, with these samples, you cannot recover, right, from this losing, even if you do not lose the sign, with d-1 samples, you cannot recover. So like something good is happening at the additional sampling. What was considered before, it was considered actually that it was proven, for example, last year that the approximate impedance passing was requiring 1.12D samples to succeed in phase retrieval. And, this kind of reduced the complexity to the IT optimum. And also it was, actually became noticed after a few months after the paper was posted, it was actually independent work has already established it via LLL. But it was, kind of, at least some part of the community is given some new information about the complexity that actually does not it does not have a computational statistical gap, this problem. Second thing is the original CLWG problem I told you with no noise. Okay, what is this problem again? So you're receiving xi.w, you multiply by some gamma, gamma doesn't matter, and you lose the fractional part, the integer part. Okay, if you're given access to these samples, IID, how many do you need to recover W? Now, there is no additional noise, so we do not have crypto hardness. So I think, you can apply the cosine because the cosine does not care about the integer part. You get a sample of the cosine neuron again. And with d+1 samples are enough. Again, the best result was from the original CLWG paper when required d-square samples, again, one application. So this kind of also improved with this, the state of the art in the, what you can do with the continuous learning with errors. And, again, this is, even if you didn't have a mod 1 operation, you have linear equations, you require d-1 samples. So even if somebody hides for you the integer part, it doesn't matter. Like there is a polynomial time algorithm that can do this, which I think algorithmically interesting. It's probably algorithmically interesting if you do not care about the statistics or cryptography at all. Okay, so how do we do this? So a few words on how do we do this. So I told you we are building a connection between cosine neuron learning and random subset sum. Okay, why random subset sum? I will explain this in a moment. Let me tell you a little bit about random subset sum. So why do we even care about random subset sum? Isn't subset sum a hard problem? So actually, given weights, what is the version of the subset sum? First of all, I'm going to be considering. So the subset sum is the following problem we learn also in first year algorithm class. You're given some weights Q1 and QD, and for the promise version, I'm telling you there exists unknown subset S, and you're observing the sum along a subset of the weights. And the goal is given the weights and the y, which is the output of this summation over these specific weights, can you find which subset you added? Okay, so this is called promise subset sum. It's a very hard problem. I mean, no surprise to this. But nevertheless, it has this, I think, fantastic thing that if you make random assumption, generating assumption on the QIs, you can actually solve it in polynomial time via LLL. So like this has this interesting kind of characteristic that in average case, for some input distribution, it becomes easy. And this is the breakthrough work in the 80s by Lakarios, Otlisco, and Friis. And it has a lot of implication, of course, in cryptography by itself. Okay. Let's see a little bit more what type of random assumption on QI this allows to LLL to solve it. So the assumption is as follows. So it may seem a little bit strange. So first of all, there are integer weights. They're considering only integer weights. And they're considering weights which are integer in a IID in a super large uniform in a super large domain. Okay, so this may take a few moments to get some intuition of why to do this. But so the weights are like, just QIs, and each QI I'm sampling uniformly from a huge number of possible numbers, like 1, 2, 3 until 2 to the d-square. So d-square bits at random per coordinate. And then, you receive y, which is a sum along an unknown subset of the QIs. You can algebraically also say it's q times w, the inner product, where w is the indicator of the subset, so a hidden binary vector. And the question is, can you use y and q to recover w? And what was this kind of fantastic idea they had is you can use y and q to construct a certain lattice that has, lattice in the previous sense, so like a lattice in actually d+1 dimensions, but doesn't matter, that has kind of two great properties for LLL to work. So it's the perfect playground for LLL, if you want. First, the shortest vector of this lattice, non-zero vector, is w, up to a sign flip. So somehow, if you are able to solve the shortest vector problem to optimality for this lattice, you are done. Like it's they can construct lattice with high probability the shortest vector is w. But okay, LLL cannot find the shortest vector problem. So like it doesn't output W, it cannot output W. And also like you have this problem, it will output a short vector that like it's at most 2 to the D over 2 times the norm of W. But like what will happen is that, you cannot avoid, this lattice has this characteristic. So first of all, it's a lattice. So if W is in the lattice, 2 W is in the lattice, 3 W is in the lattice. So you cannot avoid having this line, around 0. But somehow it has this thing that like, even if you go at 2 to the D over 2 times W, and you take the ball around this radius, it will not hit any other element. Somehow it's super isolated, the line passing from 0 to W, even at a very, very large radius. And therefore, LLL will output something which has, norm at most 2 to the D over 2 times the norm of W. So it will necessarily, LLL will hit this line. And then you can scale it down. Okay, this was kind of an easy, and here it's binary, the W, so you can obviously like recap the W. Okay, so that was the fantastic application of this. I don't have time, obviously, to tell you the technical details, though it's really a proof from the book. Especially, I encourage you to read the Freeze result if you want a cute, very nice 2-page proof of this result. And it's a technical remark now. I want to say kind of morally in the language of these days, what this is employing. It really used the integrality fair, but also it really used the fact why IID uniform in a large domain. It really used the idea that like QIs are very anti-concentrated. So like somehow, if you have a uniform distribution in a large domain, it does not put a lot of mass in any point, right? It's at most 2 to the minus D over 2 to the minus D squared at every point. And the same thing with non-linear combinations of it. So if you take a non-trivial combination, linear combination of the QIs, it assigns at most 2 to the minus D squared mass at every point. It's an easy exercise to think of. And this is really what it uses. So anti-concentration is really what it needs. Okay, so now let's go back to tell you a little bit of how we connect the dots. Like this was random subset sum. In principle, has nothing to do with cosine neuron. Yet it kind of does. So like okay, what's the setting again? We have this unknown W we're trying to find here. And we have T+1 samples coming from IID isotropic Xi, and we're observing Yi, and let's say completely noiseless. Even we can tolerate a little bit of noise, as I told you. So cosine of 2 pi gamma Xi dot W, and we have T+1 of them. Okay, so truth is, it's a little bit complicated to do cosine, so I will do actually phase retrieval. So like phase retrieval is a strict Linear problem, as I told you, where you are losing the sign of the dot product. Cosine also loses the period, right? So if you want to invert the cosine, you have to decide on the sign where you're going, and then you have a period of where you end up. So like there's another unknown that I will deal at the end. But like for intuition, let's focus on phase retrieval. So noise phase retrieval. So like somebody's hiding from you the signs. Okay, what does this have to do with random subset sum? So equivalently for phase retrieval, what you need to recover is the hidden signs. So you need to recover the epsilon i's, which are -1, 1, so that somehow you're seeing yi, which is not what you wanted to have, gamma xi dot w, but epsilon I times gamma x dot w, xi dot w. But you do not know, of course, epsilon I, right? I'm just telling you there exists this epsilon I, that this equality holds. Okay, and of course, gamma, you do not know gamma as well, but gamma can be pushed in W. So like if you knew epsilon I, because you know yi, you have linear equations here for gamma times W. So you can invert and find, have D+1 equation, so you can invert and find gamma times W. And of course, the norm of W is 1, so you can find W up to a sign flip. So like really, it's all about learning this epsilon I. If you knew the epsilon I, it's Gaussian elimination of the game. Okay, but how do you learn this epsilon i's? I mean, you have also the W's here, and that's kind of what we do. So you learn epsilon I via random subset sum. So let's say how you do this. So first of all, okay, and the reduction is as follows. Because xi's are D+1 vectors in a d-dimensional space, there exists a way to combine them to make it 0. Okay, so there exists lambda I, so that the sum of lambda I xi is 0. And the lambda i's are just, by Cramer's rule, it's just determinant over determinant. Like we can find from the data what lambda is. So we know xi's, all the xi's, we can compute the lambda i's with an easy algorithm. Okay, so we can find these lambda i's. Then now let's consider this quantity, which is the sum overall I from 1 to D+1 of this following quantity. How do you get rid of W? That's again the goal. You take epsilon I you don't know, lambda I you know, and yi you know. And let's consider this summation. Where does this sum to? Okay. Let's plug in yi here, the value of the yi. This is just the sum of epsilon I squared, lambda I xi dot gamma w. But epsilon I is plus minus 1, so this kills the epsilon i's. And we have lambda I xi gamma w, and sum of lambda xi is 0, so this is 0. So we are able, by this linear combination, to find some equation that does not involve w. Okay, so this is an equation that does not involve w and involves only the unknown epsilon i's. We know lambda I and yi, so that's kind of the trick. Okay. Where are we now? We have found a way to do from noiseless phase retrieval samples to end up with the sum of epsilon I lambda I yi equals 0, but that's actually random subset sum. Because now what you need to recover is the epsilon i's, but epsilon i's are plus minus 1. I'm telling you, I give you some weights lambda I yi that if you put plus 1 sign in some of them and minus 1 sign in some other them, all of them sum to 0. So equivalently, if you take the subset of them that are plus 1 and you take their sum, it's really half the total sum. Okay, does this make sense? So like if I give you some weights and I tell you just sign them appropriately and sum them, it's equal to 0. It's equivalent with telling you some subset of them is equal to half the total sum. Just a small algebra. And that's kind of it. So this is a random subset sum problem that lambda is yi are known. And like if you find this S, of course you find the signs, right? Recovering the sign pattern is recovering the set which are plus 1, the signs. Of course, are we really cheating here? Yes, we are. I mean, these lambda yi, first of all, are not integer. Okay, so like what I'm saying, lambda is yi, yi is this. Lambda i's are even worse ratio of determinants. Okay, so these are not I integer, good. We had some later work in 2018 with David Gamarnik, where we leverage this thing to do ID continuous for a completely different reason. Good, so the continuity is solved, but that was okay, but it's not IID still. The QIs are very dependent in this setting. So lambda i's depend on all the xi's. But yet, what I told you, anti-concentration is really what matters. So like we need certain anti-concentration property that with a lot of work you can still prove, because lambda i's are not terrible functions. They're still determinants of the data. They're polynomials of the data. So we use certain analysis tools like Carberry-Wright from mathematics, and we're able to make this work. Okay, and then what's going on with cosine, right? This is phase retrieval. Okay, so cosine to invert is a little bit more complicated because it has this unknown integer period. But yet we can carry this reduction, as I said it basically, with a small tweak at some point, and it really will give you not a random subset sum, a random integer linear equation. So it will give you weights which are random, but then some integer combination of them is equal to 0 because the periods are also hidden there. But somehow, like even this result, and of course this result here, is able to handle even small integers. So like, or at least not exponentially large integers in this. So somehow like this is how we are able to do the cosine. But morally, the whole random subset sum reduction is carried in the phase retrieval. I think that for intuition is clear enough, hopefully. Okay, so this is the two results. Again, I want to stress that this is happening with the help of cryptography. Like both the hardness is not something we are, like usually in this community using, like this worst case gap SVP hardness for inference problems. I think that's new, or not new. It's relatively new. There exists, of course, results in the literature, but it's relatively new, especially for a generalized linear model with Gaussian input like this. And also I think this is new. So like it's relatively new. So like the idea of like using a famous algorithm in lattice theory, which of course in cryptography is very known to be super powerful, and inference is not as known to be super powerful. And I think with this connection with random subset sum, we're able to leverage it, and we have leveraged in the past also for other problems. I think it's interesting. So let me close with some open problems. Okay, so the first question is, as have been asked during the talk also, right, is adversarial noise really necessary for this reduction? Morally, or at least like if you just do the reduction, you see that it's really random, the noise, but the variance position dependent. So like it's not the classic random additive Gaussian noise with variance 1, let's say. So the variance a little bit changes per W, per xi, so okay. I think it's a nice open problem. Can you get like a pure random noise? The second thing is like, okay, I mean, we have this landscape. We can have also this much more standard tools, like for understanding computational hardness in inference settings. There's a question: do standard models like low degree, SQ, sum of squares, or overlap property like give something meaningful in the regime that's agreeing on this? My bet would be that like it would give it in the inverse polynomial regime, let's say for the noise, but like somehow it will not be able to see this low noise phase transition with the polynomial time algorithm. That's LLL. So like because exactly for the robustness properties that LLL does not satisfy, it will probably not see this last phase transition. But I don't know. So it's an open question that I think would be interesting to see. Of course, this WordGap SVP harness is, I think, new for this specific inference generalized linear models settings. It would be nice to explain other gaps like this. And generally, it's a question: is CLWE really a useful start for more reductions? This paper is answering potentially yes, but it remains to be shown if like we can use the CLWE again in even problems that are even further than looking like CLWE, like the cosine neuron. And finally, LLL is a powerful algorithm, and it has really solved optimally noiseless the cosine neuron problem, the phase retrieval problem, integer regression back in the 2018 with David. Some recent work, we saw that we can solve the Planet hypercube vector in the subspace and close the gap also for this problem. And it would be that people were believing that's actually kind of a hard problem. And this work with Joan Midja and Alex. And we'll see other applications for learning inference. And thank you very much.
Great, thanks a lot, Julius. Any other questions? I have one kind of technical question, but maybe I'll ask you after.
Sure.
So let's thank Elias
Yeah.
again.
Thank you very much.